Now we are ready to write down the arithmetic coding algorithm, assuming infinite precision. That is, we are assuming that we can add and multiply real numbers exactly. Now, of course, this is a totally unreasonable assumption. If you're actually going to implement this algorithm, like on a computer, for example, you will never have infinite precision. But it's useful to look at the algorithm in this case because it's conceptually simpler than the finite precision case. Later, we'll look at the finite precision case, and the basic ideas in the finite precision case are the same. The basic way that the algorithm works is essentially the same, but there are some thorny numerical issues that pop up that have to be dealt with, and they just complicate things. So let's think about the infinite precision version. So here it is. So let's set things up first. So let's let x be our source alphabet, and it's going to be some finite set. But let's go ahead and number the elements of this set 0 to n. And let's designate 0 to be our end of file symbol. So we're going to do the end of file symbol convention. And we're going to have some probability mass function on this set. So we're going to have some p0, p1 up to pn. And this is some probability mass function, some PMF on this source alphabet. Non-negative numbers that sum to 1. Now, let's define certain quantities that will be useful in the algorithm. So let's define, I'll say it this way. Let's define c. We're going to define this vector c. c0 is going to be 0, and cj is going to be the sum of the p's up to pj minus 1. Note the minus 1. And this is for j going from 1 up to n. So let me note this. This is j minus 1. Now, let's also define, so this is the same as that c vector we defined earlier when we were doing example 2. Let's also define a vector d. So dj is going to be cj plus pj for j going from 0 up to n. So dj is just, so actually c, what is it? C j plus 1. Okay, and now we need some sequence to be encoded. So let's let, maybe I'll put that up here. Let x1 up to xk, I'll put commas. So we have some symbols from our source alphabet that are non-zero, and let's call xk plus 1 0. So the sequence that we're going to encode is x1 up to xk plus 1. All right, so now that we have things set up, let's write down the encoder. So this is going to be the encoder part of the algorithm. And the input to our encoder will be the following. We're certainly going to need the sequence to be encoded, the sequence of source symbols, x1 up to k plus 1. And we're going to need either p, let's go ahead and say that we get c and d. We could always compute c and d from p, but let's just go ahead and say that those are pre-computed for us. And now let's go through the actual steps of the encoder here. So the first part is the first conceptual part, where we find the interval from a to b. So maybe I'll call this a. So let's initialize a and b. A is 0, b is 1, and we're just going to we're going to narrow down that a and b until we get to the correct interval. So for each symbol in our sequence to be encoded, I going from 1 to k plus 1, we're going to update this a and b. So let's define w to be the current width of the interval, of the current interval from a to b. And then we'll define a new a and b in the following way, just in the same way that we did in those examples. So b is going to be a plus w times dxi. So here, this d, if you think about, go back. Well, let me finish writing this and I'll explain what's going on. And our new a is going to be a plus wc xi. So this is the, remember, xi could be some number from 0 to n. Xi is an element of this source alphabet. So dxi, so say if xi is say 2, then dxi is d2. It's the tooth element of this d vector. And similarly for cxi. So what's going on here? So this is actually the whole first part of the algorithm. The first conceptual part is just this little for loop right here. So what is this doing? Let's go back up to our example, way back up here to example 1. So we are initializing our a and b. This is our initial a is 0 and our initial b is 1. And then c and d, c, so c0 is 0, c1 is here, c2 is here, c3 is here, this is c0, d0 is here, d1 is here, and d2 is here. Oh, there is no c3, sorry. And so when the first symbol was a 2, which it was in this example, then we narrow down a and b in the following way. Algebraically, we could write this as the new b. Well, b stays the same, so b minus a is the width of the whole thing, which is 1, and then we multiply. So we take a, which is 0, plus the width w, which is 1, times d2. 2 was the first symbol, and that's just 1. It just stays the same. And the new a is going to be here. It's going to be 0.6 after the first step. And what is that? Well, it's a, 0, plus the width of the whole thing times c2, right? So it's just going to be exactly c2 in the first case. At the next step, we're going to, our new width, so just to remind you back down here, way back down here. So that was all we did in that first, when I was 1. We figure out the width, it's 1, a plus 1 times 1, and then a plus 1 times 0.6. So after the first step, a is going to be 0.6 and b is going to be 1. Now at the second step, our second symbol is a 1. So what's going to happen here, way back up, is that the new width is going to be 0.4, right? It's going to be the width of this thing. So that's w. And so so now at this step, well, if you think about it, maybe if you think about it, it's all going to work the same way, because we're going to have the width is p2 times, here this would be p2, this would be our new a plus p2 times c0, and this here is going to be our new a, 0.6, plus the width p2 times c1, and this is going to be a plus w times c2, and so forth. So it all recovers. So this recovers the original thing that we wrote down. All right. And now we need to do the next part, which is to find the binary sequence, find a binary chunk that's contained in that AB. So this is conceptually part B. So let's initialize. Let's use our S. We're going to have our S counter. Initialize that to 0. And we have the following 3 cases. So I'll just go ahead and write this down, and then I'll briefly explain what's going on. So if we're in either case 0 or case 1, so if, I'll put it this way, if B is less than 1/2 or A is greater than 1/2, these are the cases that we wrote down, then if b is less than a half, do the following. This is case 0. Emit 0. Our new a becomes 2a, and our new b becomes 2b. And then there's going to be more, but just to remind you, this is exactly case 0 up here. b less than a half, where in this case, emit 0, multiply everything by 2. And in the other case, when a is greater than a half, emit 1, and multiply 2 times a minus a half, and 2 times b minus a half. So this is case 1, and then this is otherwise, else, if a is greater than a half, emit 1. A becomes 2a minus a half. B becomes 2b minus a half. Okay, and now, so that's the sort of what we described when we were thinking about the process in this way. What we said was that we're going to have some sequence of cases 0s and 1s until we straddle the midpoint, and then we're going to have to do case s some number of times. We're going to blow up the middle half of some number of times. We're going to count how many times we do it. We're going to increment our s. And then at the end, we're either going to emit 1 and a bunch of zeros or 0 and a bunch of 1s. So we're going to end up in in either the third quarter or the second quarter. So when we straddle the midpoint, so when that first while loop terminates, then we will be straddling the midpoint, because by definition, if we're not in either of these two cases, then we're in this case. Well, we're at least a is less than a half, and b is greater or equal to a half. So we may need to do some number of these, and let's write down what happens then. So we have another while. Let me put that a little bit more green, maybe. Okay, while a, this is case s, a is greater than a quarter and b is less than 3/4, then do the following. Increment s, case 0, or rather case s. Increment s, a becomes 2a minus a quarter, and b becomes 2b minus a quarter. So we do this some number of times. Remember, we initialized s to 0, and then at the last, so back up to our diagram here. We do this some number of times. We blow up the middle half until we're in one of these last two cases. Either we contain the third quarter or we contain the second quarter. If we contain the, let's say this one, if we contain the second quarter, then we increment s one more time, and we emit 0 and s1s. And if we're in the third quarter, then we increment s, we emit 1 and s0s. So we may as well, in either case, we're going to increment s. So let's go ahead and do that. And then let's check. If a is less or equal to 1/4, then we can go ahead and say that we're in the q case. This is case q. Emit 0, 1, 1. So this is going to be s1s. And otherwise we must be in the other case. We must be in case 3q. So we emit 1, 0, 0, 0, s0s. 1 and s0s. So let's annotate these. So as I was describing that, I mentioned which cases they were, but let's go ahead and annotate these. This one here, this is case 0. We emit a 0. This is case 1. We emit 1 and rescale in this way. This is case, we called this case s. We increment s and blow up the middle. This one is case q. And this last one is case 3q. So this completes part B of the algorithm, where we found the binary sequence that was the shortest possible binary sequence, or a shortest possible binary sequence. It's not necessarily unique. A shortest possible binary sequence where the corresponding interval, the corresponding chunk, is contained completely within the interval from A to B. And so at the end, so now we are finished the algorithm, and the output is just the sequence that we emitted. So it's this, whatever that sequence of bits that we emitted. I'll call it beta 1 up to beta m for some m. So it's the sequence emitted during this process. So that completes the description of the encoder in the infinite precision case. So just to be clear here, the notation maybe, so I'm using sort of Python notation. It's sort of a pseudocode, but indentation here indicates the looping structure. So this for loop, so maybe just to be explicit, this for loop contains these lines. This while loop contains these lines. This while loop is just this guy, and so forth. Okay. So that's the encoder, and next we will do the decoder.